just a quick, let's go for the agenda of today's webinar. So we will start with an introduction to power electronics by my colleague Thomas Crémou, who is our decarbonization and mobility projects manager. And then I will give the floor to Mansour Nyang, who is a power electronics engineer from Technology and Strategy Group, and he will dive into the role of power electronics in electric vehicle efficiency and sustainability. We will then have a Q&A session, but please feel free to write your questions in the chat if you have any. So just a quick presentation of E-BOOST. So E-BOOST is a European funded project which aims.
We lost you, Noémie.
Yeah.
Yes, it's good.
Yeah, sorry, I had a connection issue for a couple of seconds. I hope you can hear me now.
Yes.
Okay. So, E-BOOST is a project that aims at supporting SMEs from the electromobility sector in strengthening their resilience, green and digital transformation, and internationalization activity. And behind this project, there are 6 clusters dedicated to mobility from 6 different countries, including Cara. So about the next opportunities within the E-BOOST project, on the 9th and 10th of April, we are having an investor and sponsor day. So it's a 2 days event. The first one is free participation to the Drive Forward conference, which is a fair dedicated to the future of the automotive industry. And the second day is we are organizing a pitch sessions for SMEs in front of investors, and also a visit to the powertrains test center, TNO. So if you are an SME from the electromobility sector, you are eligible to get 1,500 euros to come to our event. So quite nice, right? And you will have the link thanks to my presentation to apply if you are interested. Next opportunity is a B2B event which will take place in Zaragoza on the 22nd of May, and we are also organizing site visits to a bearing company and other companies from the automotive and mobility industries. And same thing, we are opening the call today, and you will be able to apply and get a lump sum to participate, to cover your expenses to go to Zaragoza. Last but not least, in June, we will have our International Business Forum. It's a B2B with companies from USA, Canada, Turkey, and Europe, and it will be online, and the date is still to be confirmed. So if you want to know more about these next opportunities, please follow us on LinkedIn, E-BOOST project, and also I think you all receive Kyra's newsletter, so you will hear about this more in our newsletter. And so now, without further ado, I will give the floor to Thomas for an introduction on power electronics.
Thank you, Noémie. Here my screen. You see me if you want, if you will see it. So hello everyone. I'm in charge of energies for Cara. Cara is an European cluster for mobility solution. Here you have some key numbers about our local ecosystem. Rhône-Rhône-Alpes region is the first industrial region in France. It represents 15% of French unemployment, 500,000 employees, and the region shelters 11,000 automotive companies. Below you have some key players of our region. Our network represents 400 members, from laboratories to big companies with collectivities, with TNS engineering, for example. The aim is to help them to meet each other and transfer knowledge through business and technical events. As, for example, of technical knowledge, here is a major issue of mobility sector, power electronics. What is power electronics? First and foremost, which vehicles are concerned? Here you have new vehicle market temporal evolution for light vehicle on the left and heavy vehicle on the right chart from 2020 to 2030. Red squares show motorizations which need power electronics. We see that it represents at least 2/3 of the vehicles. What is power electronics? Power electronics is the application of electronics to the control and conversion of electric power. Its principle is based on the kind of automatic and controllable switches named semi-conductors. Many technologies exist with advantages, high voltage, for example, and drawbacks, cost for GaN, for example. These semiconductors are surrounded by other components in order to create the base units, AC to AC, AC to DC, inverters, etc. These units need softwares, bus bars, printed circuit boards to work in order to form applications such as electronic network to produce energy from renewable energies, distribution, management, energy storage. But new issues appears to ensure the grid stability, therefore constant frequency, like vehicle to grid, energy storage on the grid, and etc. But some challenges gravitate around these components application until the nanoscale semiconductor. Mr. Nyang is going to describe some of them. Mr. Nyang, the floor is yours.
Thank you, Thomas, for the introduction. I will let my colleague Martin to present you.
Do you show my screen?
Yes.
Yeah, it's okay. So yes, first, hello everybody, and thank you to be connected for this technical webinar. Today, we will speak about power electronic in electric vehicles and their role in efficiency and sustainability. Before going deeper in this subject, I will just give you some information about TNS Group. Technology and Strategy is a French company specialized in embedded systems. With almost 20 years of experience in transport and energy, we offer a wide range of services around digital, consulting, and our bigger business unit, engineering, to address small companies to big groups. Our 400 people in engineering division allow us to focus our development on results commitment projects. And today, we are leading 50% of our projects in our design offices. I will not spend too much time here to develop all our technical expertises for this short webinar. To summarize, we have 2 design offices in France specialized in industrial systems with all the technical expertises that you can see on this slide. With our design office in Alsace, near Strasbourg, we can develop completed products from design from scratch to industrialization and production. We also design and produce test benches in this office. And in Lyon, we can support our customers for all their projects V-cycle, from writing the specifications to support them with the certifications of their products. The last 5 years, we supported car manufacturers around high power projects. Eaton with the DC-DC converter 9 kilowatt validation for trucks. Garrett with test and qualification of a water cooler inverter and integration of ASPICE hardware. Punch Powertrain with a service center of 30 people, and Symbio in hydrogen environment subject, for examples. Here you can see our meanings for our 2 design offices. In Lyon, we can test and analyze systems up to 20 kilowatt with 3 benches in mono and triphases, and 2 climatic ovens for humidity, cold and hot tests. In Strasbourg, we have more important meanings with climatic chambers, a machining and prototyping area, and a montage area. As you can see, we have a real expertise in electronic systems. And now it's time to let Mansour speak about the real subject.
Thank you, Martin, for the brilliant presentation. So I will represent you the role of power electronics in electric vehicle. First of all, I will say hi, everyone. Thanks for being here. Today, I want to talk about something that's often invisible, but absolutely essential in electric vehicle. I like to say power electronic. It's what make EV perform, what help us to go further on the charge, and what connect vehicle to the energy system around them. We will look at how this technology works, the key component behind it, the challenge we face, and what's coming next. To keep things simple, here we will start with why power electronics matter in the electrical vehicle, then move into the main component, the technical and costly challenge, and then dive into some of big innovation like semi-conductor, 800 voltage system, even how EV can give power back to the grid, and all of this in complete safety. I will keep it practical as possible with example you have probably seen or hear of. So why does it matter? In an EV, the battery stores energy in DC, but the motor needs AC. The inverter handles that conversion. Without good power electronics, you will lose a lot of energy as heat, which means shorter range and poor performance. It's also enabled regenerative braking, where the motor becomes a generator and send power back to the battery. It's one of the way EV get more efficient in stop and go traffic, for example. And all of this support broad goals like reducing emission, integrate renewable energy, and pushing forward that energy. Now, let's break down into components. First, the inverter. It's the heart of the propulsion system. It controls how power flow to the motor and back from it when braking. Then, we have the DC-DC converter that's like a translator between the high voltage battery and low voltage system like lights, screens, and sensor. And finally, the onboard charger. It converts AC from the grid into DC to charge the battery. In V2G capable car, it can work in reverse, sending energy back to the grid. Together, this part manages how energy moves through the vehicle. One of the biggest goals is reducing energy losses. You have to know that. With traditional silicon, we lose about 5%. With the new material like SiC, losses dropped 1 to 2%. That's more range, less heat, and smaller cooling. But new tech isn't free, as you know. SiC is 3.5 to 4 times more expensive than standard silicon today. It requires design change and careful thermal management. The flip side is that it lets us shrink the whole system. Smaller inverter, less weight, better packaging. Overall, it's a trade-off between cost and performance. Let's dive into deeper SiC and GaN, what they are and why they are better than traditional silicon. First, structurally, silicon carbide, normally calling SiC, is a component of silicon and carbon. It has a wide band gap, about 3.26 eV. That's 3 times higher than silicon. This means it can withstand higher electric field, operate at higher temperature, and switch faster. It also has better thermal conductivity, about 3.7 watt per centimeter per Kelvin versus 1.5 for silicon. And for nitride gallium, GaN has a band gap of 3.5 eV, which also allow for high frequency, high efficiency switching. GaN components are typically used in lower voltage but very high frequency applications like onboard charger or small DC-DC converter. So why are they better than silicon? They can switch faster, which means smaller passive component, more compact system, and higher overall efficiency. They generate less heat, so thermal management is simplified. They allow for high power density, smaller, lighter system without sacrificing performance. With SiC, we can build inverters that are 2 to 3 times smaller. I repeat, 2 to 3 times smaller and is still more efficient than their silicon counterpart. For example, Tesla's Model 3 switched to 6 MOSFET in its inverter, which helped increase range and reduce cooling need. The result, energy saving, like the vehicle, and better performance, all of which are critical to electric mobility. For the future innovation, SiC and GaN are transforming the power electronics landscape. They dramatically reduce energy losses from 10 to 15% down to just 2 to 5%. They also enable regenerative braking to recover 30 of kinetic energy during deceleration, potentially adding 10 to 15% more range in city driving. That's amazing. Now let's break it down into components. First, the inverter. It's the heart of the propulsion system. It controls how power flows to the motor and back from it when braking. Let me give you a detailed example in Tesla Model 3. The inverter is based on silicon carbide transistor. This enables faster switching, higher efficiency, and less heat, which means Tesla can reduce the size of the cooling system and increase overall range. So this inverter controls the three-phase AC motor by modulating voltage and frequency with higher precision. It's constantly adjusting power flow based on acceleration, regenerative braking, and driving mode. And in regenerative mode, the inverter acts like a rectifier, converting the AC generated by the motor back into DC to recharge the battery. Without this bidirectionality control, energy recovery will not be possible. So the inverter is not just a converter, it's a real-time brain for propulsion. Now let's talk about the DC-DC converter. They make the DC-DC converter more efficient, 5 cutting auxiliary losses by 10 to 20. This advantage make wide band gap semiconductor a cornerstone for future EV platform. Let me give you an example. The dual active bridge, or DAB, this type of DC-DC converter is becoming increasingly important in advanced EV architecture. The DAB allows high efficiency bidirectional power transfer between different voltage levels, for example, between a high voltage battery and a low voltage auxiliary system, or between the battery and the onboard charger, for example. What makes it special in its high efficiency across a wide power range and the ability to handle fast, isolate, bidirectional transfer, which is ideal for V2G. Battery swapping or energy reuse between traction and auxiliary system. It also supports galvanic isolation, which adds safety when interfacing with the grid or different subsystems. DABs will play a vital role in managing energy more intelligently and efficiently. As you can see, the market is responding. Here a chart showing projection from 5 major sources, including OIOL in Villeurbanne in Lyon, and FMI and market research future. You can see a strong upward trend, not just short term, but sustained through 2035. This reflects both the performance benefit and the growing confidence in manufacturing scalability. So this isn't just a lab trend. It's happening in the market and very fast. Another shift we are seeing is vehicle architecture for future trend and innovation. Most EV today run to 400 voltage. Moving to 800 voltage cuts current in half. You can see it in your right, which reduce heat and makes the whole system more efficient. This means thinner cable, less weight, up to around 25 kilograms saved just in wiring. That's amazing. And this also reduces copper uses, which contribute to sustainability goals. More importantly, it enables ultra-fast charging. Porsche Taycan and Hyundai Ioniq 5, for example, can go from 10 to 80 in under 20 minutes on 350 kilowatt range charger, which is game changer for EV adoption. 800 voltage also means better integration with future charging infrastructure, especially high power DC charge designed for commercial vehicle and long distance EV. In terms of thermal performance, lower current means reduced losses by a factor of 4 because power loss is proportionally to current squared. That significantly simplifies thermal management and increases overall system efficiency. We are seeing more manufacturers like Lucid Motor, Kia, and even Tesla preparing platforms that either support 80 voltage or can scale to it in the future. So 800 voltage isn't just about charging speed, it's about optimizing the entire electrical architecture for performance, for packaging, and future proofing. Let's zoom about this, think beyond the car itself. What if your EV wasn't just a consumer of energy, but also contributor? That's the question. That's the idea behind vehicle to grid or V2G. With V2G, your car doesn't just take electricity from the grid, it can also give it back. Imagine charging your EV at night when electricity is cheap or from solar panel during the day. Then using that stored energy to power your home or even support the grid during peak hour. Technically, this is enabled by a bidirectional charger and a smarter energy management system. The car becomes a mobile energy storage unit. For example, you have a 16 kilowatt hour battery can power of a home for 2 to 3 days. It depends for the consumption. I will show you another European project who are developed in Denmark. This initiative launched in collaboration with Nissan, Enel, and Nuve, establishing the world's first fully commercial V2G hub in Denmark. The project involved installing 10 V2G units at the headquarters of Danish Unity, which also purchased 10 Nissan ENV 200S. That is the model of the vehicle. These V2G enabled electric vehicles were utilized to provide power capacity service to the grid operator. Driver could earn up to 1,300 per year by supplying the grid during peak time. It can be interesting for France. During period of high electricity demand, typically in the early evening when people return home, cook, and turn on appliance, the electrical grid face peak load condition. This peak require expensive, fast-reacting backup power source like gas turbine, or risk overloading local infrastructure. Now imagine thousands of EV plugging in during the same windows, each with a battery storing 14 or 16 kilowatt hour of energy. In even a fraction of those vehicles discharge a few kilowatt hour back into the grid, we could deflate that peak significantly. And with new European rule pushing for V2G interoperability by 2025, this isn't science fiction, it's already happening. Before concluding, it's worth highlighting another important topic: safety and standardization in EV power electronics. As voltage and switching frequencies increase, especially with aging voltage architecture and wide bandgap semiconductor, ensuring electrical isolation, thermal protection, and electromagnetic compatibility become more complex. We are seeing the rise of new standards around high voltage interlocked system redundancy and fault detection. Functional safety framework like ISO 26262 are being standard to cover high power converter and V2G enabled architecture. Standardization is also key to enabling interoperability, especially for charging and bidirectional system. Protocol like ISO 15118 are becoming critical to allow vehicle to communicate securely with charger and the grid. So the future of electrical vehicle power electronic will not just about performance, it will be about trust, safety, and seamless integration. So to wrap up, power electronic is more than a technical detail. It's what makes EV perform well, charge fast, and integrate with the energy system. With advance in material, power platform, and grid interaction, we are moving toward a smarter, cleaner transport model. So thanks for your attention. I'm happy to answer any question. Thank you. Back to the presentation.
Thank you so much.
It seems that we are all French speakers, so if you want to ask your question in French, it's possible. It seems that we have no question today.
I guess everything was crystal clear.
You have a question concerning V2G. We know that there is the Renault 5 from Renault. What you think about this kind of V2G? It's a V1. I know a V1 of V2G. No real V2G.
Excuse me, can you repeat the question, please? In French?
You know the electric vehicle Renault 5?
Yes, I know the Renault 5.
Yes, Renault 5 enables vehicle to grid.
Yes.
But I know that it's not a real vehicle to grid because it needs to have a contract with Renault, and Renault it's difficult to have money with the vehicle to grid from Renault 5. No, you don't know.
So we can't hear you. Maybe I mean your microphone is muted.
I'm
And
sorry.
also we haven't had a
Sorry.
chance to see you either. I don't know if you want to turn your
I'm
camera
here.
on.
I'm just here. So to respond the question, to answer the question of Thomas, to be able to push energy in the grid, you have to get some certification from EDF. So and you have to respect some standard and to be authenticated for that. That's why the Renault 5 can be using for V2G actually. They also embark the system, but it's not nowadays. It's not can be used for V2G.
Okay.
Any other questions?
Just to make sure to understand, that means that the Renault 5 has the option, but it's not yet implemented due to the fact that they haven't the agreement from the grid from Enedis to use this system, or?
Yes, that's
okay.
it.
So it's maybe just a question of time.
Yeah, just a question of time, because we have some European rules who encourage V2G using in this year 2025.
Okay.
So we can hope to see it this year.
And we speak about software-defined vehicle and one-chip vehicle. Do you think it could be possible to have all power electronics applications on one chip, or not?
All of one chip, it's difficult to say that now, because in power electronics you have different range and different application in the vehicle. So example of the DC can manage a different level of voltage and different part of the vehicle, and we can use that in some case, and for the other we can't for the problem of manage electromagnetic compatibility, we can use all in one pieces.
Mm-hmm.
Another question, maybe in order to optimize the efficiency, we speak a lot about heat transfer for power electronics devices. Is there any system that can get the heat from this power electronic device in order to warm the vehicle itself. I mean, to warm the interior of the car for getting heating for the driver.
As I know, it's not using is the actually car for the question of weight, because reducing this type of heat transfer and by using some new semiconductor, allow the manufacturer to make a lighter car, so they can be used more space and more other application for the system. That's why they are not using it now, but it's a good point for the manufacturer, I think.
Okay.
That's all, I think.
And maybe,
Yes,
maybe, sorry, another question regarding certification and regulation. Is there any agreement needed, like CE regulation or something like that, that you need to have for the different components? You need to have this approval from an authority giving this regulation commitment, or
You have a regulator trunk, AFER, alternative fuel infrastructure regulation, who can give some of these rules for the Europe concern to get agreement with to manage what you have to do.
but
I don't know if it responds of your question.
yes, just to maybe to give another question.
Yes.
If you want to sell your product, I mean, you are producing an inverter and you want to
Yes.
sell it, do you need to have a CE regulation patent, or not a patent, but something saying that, okay, you are respecting the regulation for this kind of component, and you are able to sell it in Europe or to sell it in the United States or in other market? And who is providing this label or this agreement to sell?
I think it's R10. They are able to give this kind of certification to the vehicle, and the manufacturer to sell in France, European, in Europe, or in US.
Okay, you mean R10 for the EMC, for
Yes.
the electromagnetic compatibility?
Yes.
Okay, but according to you, there is no other regulation or something like that to have in order to be able to sell a component?
To be able to sell component, because the different manufacturer component like Onsemi, ST, and the other are responding of some norms in this field to be in total how can I say that, in total harmony with either 26 to manage to get this kind of certification.
Okay. Yeah, I'm asking this question because I'm working at Transpolis, and we are a laboratory labelized by COFRAC, and we are providing for other system such kind of proof in order to have the ability to sell some components. It's on infrastructure for the safety road barrier, for example. But my question is to know if there are this kind
like
of norms and
this kind of like UTAC.
yes.
Like
UTAC is
okay.
one of our competitors.
One of-
Yes.
Okay. I don't hear the question on this side, because yeah, you have some organization who can certificate your product.
Okay.
In technology and strategy, we can accompany. How can I say that? This kind of supplier to get the certification for their system in electric vehicle and in aerospace.
Okay. Thank you.
You are working for one what is the name of your company? It's not
Transpolis.
Transpolis. Okay,
Yes. It's close to Lyon.
close to Lyon. Okay. Sorry.
Right to know.
All right. Any other questions? Otherwise, I will thank our speakers. And you will be receiving the slides. Yeah, I have a nice weekend, everyone, and I hope you enjoyed.
Okay. Thank you.
Thank you.
Thank you, everybody.
Thank you, everyone, and see you.